Good morning, ladies and gentlemen. Today we're going to have a look at the characteristic curves of a diode. On the Cartesian plane here, it's V forward. V forward, V reverse, I forward, I reverse. Now on this Cartesian plane here, as you may have seen on your textbook, this voltage in here, if it's germanium, when it arrives at a voltage of 0.7, current start to flow here. But if it was if it's silicon, it's 0.7, but if it was germanium, at 0.3 there. Now that is on this first quadrant. How's our diode? It is forward biased. And this here, when we reverse bias our diode, the broken line here tried to show you that we increase the voltage to a certain value, which we'll refer to here as V breakdown. V breakdown. Our diode start to conduct in here. A lot of currents flows. Now this, we're going to talk about it. This is when it is reverse bias. Here it is on the first quadrant, it's when it is forward bias. Now remember, a diode gets reverse bias when the voltage across it is on the anode, it's more negative than it is on the cathode. Now looking at this Cartesian plane again, guys, it is very, very important for you to be able to draw this characteristic. This was for silicon and this for germanium. This breakdown point, we're going to talk about it lengthily in other types of diodes later on when we start analyzing them. Now very, very important for you guys is you must be able at the end of this to understand this. This is the VI voltage. VI characteristic, voltage current characteristics of a diode. It is very, very important for you to be able to draw these characteristics and really understand them. This voltage, would talk about it, this breakdown voltage. It's a very critical voltage which you must take care of. Now next, what do we want to have a look at? We want to have a look at the diode approximations. Diode approximations. Now what are diode approximations? These are models which we use to explain the behavior of a diode. Now I'll have two circuits in here. The two circuits which I'm drawing in here, the only difference is VB. Circuit A, when you look at it, to the anode we have connected positive, and circuit B to the anode we have connected negative. We therefore say circuit A is forward biased. Never write this FB, please. And this one, how is it? Reverse bias. Circuit B. Circuit A is forward bias because positive is connected to the anode and negative to the cathode. Now we're going to look at these two circuits using the models that are, what is a model? It's a system or connection of facts or some demonstration of an explanation in a way that would understand it. The first model that we're going to look at, we call it ideal model. What is an ideal model? We're going to have a look at it. We're going to have a look at this diode. In the ideal model, very, very important, in circuit A, how is our diode? Our diode looks like it is just an on switch. An ideal situation, we say when positive is connected to the anode and negative is connected to the cathode, a diode acts like an on switch. Now, very, very important, you just see a diode as an on switch. Despite in the characteristics, we talked about the voltage being it has got a 0.7 volt. But look at this one. This one, we see it as an off switch. Circuit B, because negative is connected to the anode and positive is connected to the cathode. Circuit A, if we were to draw it and draw it, this is the equivalent of the diode. The equivalent of the diode. If we were to go back to it, guys, now what happens when we draw the characteristic curves? Don't forget again, this is V forward, this is V reverse. And what is this? I forward. And what is this? I reverse. Now, going back to it, we're going to have a look at this one. When it is on the first quadrant, here it is. Sorry. In other words, it is just a switch which is on, current is flowing. When it is reverse bias, look at it. Now that's the characteristics of what? An approximation called what? The ideal model. Now where do we use the ideal model? Application, where do we use it? We use the ideal model when we want to explain the circuit operation. Explain what? The circuit operation. When you look at this circuit, you say circuit A is forward biased, therefore current is flowing. You assume it that current is flowing through it as it is forward biased. Now that is represented by this arrow here at the center of I forward. And circuit B is how? It is reverse bias, therefore there's no current flow. It's like an open switch. Now that's the first model that we're gonna look at. I say, where do we use this model? When we do circuit, explain the operation of a circuit. You look at a diode, you decide, is it forward or reverse bias? When it's forward bias, it's like an on switch. When it's reverse bias, it's like an off switch. Now we're gonna have a look at another model. Another model. Where is another page? Here. Oh, top there. So, thank you. I said we're going to look into another model. This model is called the practical model. The practical model. Now, the practical model, where we're going to have a look at again that diode. Remember circuit A, how is it? It is forward bias. When it is forward bias, we said to you, now we're going to draw a little equation. Now, we said it's like a battery which is forward bias. How big is that battery? Now this is our diode. It's equals to 0.7. 0.7. When it's reverse bias again, guys, remember there's no current flowing. When it is reverse bias, this is forward bias, this is reverse bias. Now the characteristic now becomes easier again. When we draw the characteristic curve of it, we have something of this is what? V forward, this is V reverse, I reverse, I forward. On this level in here, it's 0.7. On this level in here, it is 0. The voltage is 0. Now this is represented there. Now very easy again, we can start drawing the formula. Remember, this is a diode, and we have a resistor there, R, and we've got our VB there, our V bias. Now when we draw the voltage here 0.7, the voltage here would be V bias, which is VB. VR would be equals to V bias minus this voltage here. Now look at this. This is opposing those things. The voltage across the diode is opposing the V bias. Therefore, we subtract it there, all divided by I forward. The voltage across by R divided by R will give us the I forward. I forward. Now easy, straightforward. You've got your resistance there, and you do your calculation. Now once you know the current, you can know the voltage there across the resistor. You can, simplify and analyze this particular circuit. Now I've just drawn the characteristics there. These are the VI characteristic of what model? Of a practical model, VI characteristic. Now where do we use this one? When we do simple calculation. Simple calculation. What do I mean when I say simple calculations? I mean, you look at this circuit, you start looking and say, no, this diode is forward bias, therefore the voltage is 0.7. The voltage across R will be, VR will be equals to VV minus 0.7. Now these are simple calculations. But remember, in that real model of a diode, this line is not straight like it is here on this practical. Now we have another model to accommodate that. We've got another model to accommodate that. I'll be looking at it, the third model. Now what do you call this? They call it the complete model. What is a complete model? A complete model, it's almost the same as the practical model, but the only difference is, guys, when you look at a diode, when it's forward bias, you say this is the diode, it's got a voltage here. Remember, in that diode, in our model, in our VI characteristic, it had a little voltage there. Now we call this internal resistance of the diode, and this is the situation. This is your diode. Now what does this mean to you? If you want V forward, remember you had a resistor there, and you had VB there. VB, and you have R there. You can draw a little equation. You've got this R there. If I want my I forward, that is when it's forward bias like it is here, it would be VB minus V diode. Remember V diode. V diode, what is the voltage across it? It is 0.7. The voltage across VD. All divided by the sum of these two resistors, which is your main resistor, limiting resistor, plus the dynamic resistance of your diode. Now that being the setup class, another very important thing is when it is, this is when it is how? Forward bias. When it is reverse bias, guys, actually it's like an open circuit. But remember, there was a little leakage current. Now we have a resistor there in parallel with our switch. This resistor is very, very big, such that a very small current is flowing there. Now drawing the characteristic curves again of this setup, guys, it's very straightforward. Drawing the characteristic, it's very straightforward, guys. You put it on your Cartesian plane. I said this is V forward. What is this? V reverse, I reverse, and I forward. Now it goes there. When it arrives at 0.7, there's still the voltage. This is 0.7. The voltage still increases here. But very, very important, I'll show you how does it increase. In that formula, we connected, we've got, you said it's got an R, a dynamic resistance, a resistance that keep on changing. That's what makes it there to be in that fashion. Now again, remember here, we'll arrive at a certain point, which we call V breakdown, VBR. We'll talk about it, and it's connected how reverse bias here, connected how forward bias. The voltage not always 0.7, the voltage across it is VR, it's 0.7 plus VR dynamic. If you cross multiply this, you'll find that your voltage across the diode would be this voltage minus the voltage VB minus the voltage here plus the voltage here. All this we separate from V bias. Now this we're talking about a complete model. Now where do we use this model? When we do design. Now when you design a circuit, later on in your studies you're going to start designing a circuit. Please understand that when you design, you start taking our dynamic into consideration. Okay guys, we're going to look further now. These are the three models. Please look into the problems. There's an example. Check that example. Example 2.1. Example 2.1. Please check it. It's a very interesting example. And equally well as you check example 2/1, I want you to visit the problems at the end of the textbook. The problems at the end of the textbook. The ones that talk about this. Please, always when you go through your prescribed textbook, guys, always look at the heading, like section 2.4, which is a section that we'll be attending to now. I'm not going to write down the section objective, but I'll read them for you. I'll read them for you. They say here, what is it that is expected of you? Describe a basic power supply. You must be, at the end of this section, you must be able to describe the basic of a power supply, a DC power supply. Now, and they go further, determine the average value. And this should be your guiding principle when you use this textbook. Now I'm going to give you a DC power supply. We talk about a block diagram. DC power supply. Now, DC power supply. Now we're going to look first into a block diagram of a DC power supply. We've got a transformer. After a transformer, it goes into a circuit which we call a rectifier. After a rectifier, it goes into a circuit which we call a filter. And after a filter, to a circuit which we call a regulator. Oh God. Sorry. Oh, that is a regulator. Now, this is your load. this is your load. Now, that being the setup in here, let's have a look. A transformer, remember, in one of the few things, I'll draw you a transformer. We'll quickly go through a transformer, its equations, how do you go about it. A basic transformer is something of this nature. Now, normally, like I said in my previous video, normally it will be a step-down transformer. Now 10 to 1 meaning that we've got fewer tens in the secondary. This is my primary, this is my secondary. Now, meaning this is a step-down transformer. Let's have a look again, remind you of the formula. N sec over N prime will be equals to N, and then N is also equals to V sec over V prime. Number of tens in the secondary. Now when your N is less than 1, you know it's a step-down transformer. Now look at it, V sec. Remember, you're in South Africa. Whenever people talk of AC, they only talk about, say, the voltage is 220 volts. 220 volts. Now let's have a look when you have such a transformer. What would be your secondary voltage? V sec will be equals to N sec over N prime, all multiplied by V prime. Now this is equals to N sec, it's 1 over 10, all multiplied by 220. Now this cancels this, the answer is equals to 22 volts. Now remember, this is an RMS value. When you are working and you are in electronics, you've got to convert an RMS to a peak. Therefore, if I want V peak secondary, V peak secondary. What is V peak secondary? The voltage I get across here, and it's a peak. I multiply it by V secondary, which is an RMS, multiplied by square root of 2, meaning that it's 22 times square root of 2. Your answer will be straightforward, 31 point something. Please check your calculators, it will give you an answer there, 31 point something, when you multiply. Now, we have just seen how do you go about using what? Using your DC power supply. We put something in here, we still get an AC here on the secondary, but it is of a lesser value now. The peak here, it's how much? 31 volts, comma something, and the peak here will also be 31 comma something. You have just seen what did a step-down transformer. It took in 220 volts RMS, converted into 22 volts RMS, but when we want to draw it, you draw it as a peak. Now the voltage you get here, obviously here, would be the same as this voltage. Now we're going to put in a new circuit, a very new circuit for you guys. We're going to look at it. It's got a transformer. The answer here, it's 10 to 1. To 1. Remember, we said we've got 31 point something in here. Now I put another device in here and put in my load. Now, if in here I put my oscilloscope and I want to measure the voltage in here, first, let's have a look at the secondary voltage, the voltage across point A and point B. It would be something of this nature. The zero line, the voltage is here, is 31 point whatever, and the voltage here, it's negative 31 point whatever. Now now this is my V peak secondary. V peak secondary. Now the next voltage that I look at, zero line, it would be, we call it V peak out. Why do you call it V peak out? Is because it is the output. Some refer to it as V peak rectified. Why do they call it that way? It's because it's a rectified voltage. Now, during this time, it was positive here and it was negative here. How's my diode now? It's forward bias. What does it do? Conduct. And when I measure there, I'll find voltage. The next thing, what does it become in here? Negative, positive during this pulse. How's the diode? Reverse bias. So for this time, I don't get any output. Why? Because the diode, it's like an open circuit. What model am I using now? Just to see it whether it's operating, I'm using a practical model. Remember when it was forward bias, using a practical model, I'll see what is the voltage across it, 0.7. This voltage plus this voltage must give me this one. In other words, from V peak to get V peak out, you'll see V peak secondary minus how much? Minus 0.7. What does it give you? V peak out, or as I said to you guys, I said to you, sometimes it's called V peak rectified. What is it? V peak rectified is the same as V peak out. Very, very important. Now, the next one, when it becomes positive, same as number one. Now, what do you call this? This output, it's actually referred to as pulsating DC. Why do they call it pulsating? It's because it's made of pulses. What do they call it? Why do they call it DC? It's because it only flows in one direction. Either it flows or it doesn't flow. This circuit is referred to as a half-wave rectifier. Half-wave rectifier. What does it do? Rectifies half the wave. But look at it. This circuit, guys, during this time, okay, before I talk about that, if I wanted these pulses, the negative pulse, what do I do? I would connect a diode in this way and put it there. In other words, this will conduct only what? The negative pulses. But at the moment, it's connecting what? Only the positive pulse. My output, we call it pulses because it either flows or it doesn't flow. Flows, doesn't flow. Now, as you can see, I wrote how many waves there. I wrote 2 cycles there. I drew for you 2 cycles. Now, look at it, guys. Again, very, very important. I showed you V peak rectified, which in the textbook or some people refers V peak out, is V peak secondary minus how much? 0.7. If, my dear students, I had another diode there, how many diodes do I have now? 2 diodes. This diode number 1, diode number 2. I have 2 diodes and they're connected there. How much will I subtract? Ooh, I have 2 diodes. It's 0.7, 0.7. I'll subtract how much? 1.4. That's great, guys. As I said to you now, we have looked into a half-wave rectifier. Let's quickly have a look at something that is very, very important again, which is F out. What is F out? It's output frequency. In South Africa, what is the frequency, guys? 50 Hertz. Now, the output frequency would be 50 Hertz. As you see, during that time, what do we have? We have 1 cycle, another cycle later. It was 50 Hertz, this is 50 Hertz. In other words, the output of a half-wave rectifier would be how much? 50 Hertz. If you do your calculation, you find your output is something different, there's something wrong with your circuit. Another thing that we've got to calculate, class, is called V average. I always say to my students, be careful. V average is actually VDC plus V peak out divided by pi. In this case now, what is our DC? 0 volt. Look at it, our reference line is 0. If by chance our line was here, this would be the DC part. We would have a different voltage there. This is the DC. Until from there to there is the DC. Our V average will be VDC, which is this distance from there to there. Again, sometimes we do not have easy things that easy. If this is your zero line, and your pulse is something like this, how's your DC now? Negative. How's your DC? Look at it from there to there. It's how? Negative. Now always check this DC. In that first case, the DC from there to there was positive. Now always check whether your DC is positive or negative. The last thing about the half-wave rectifier, guys, is to know how to calculate. I've shown you there how to calculate an average value. Another very important class is PIV, peak inverse voltage. Now the peak inverse voltage, guys, is straightforward, very straightforward. When you do the calculation of the peak inverse voltage, always be careful. The peak inverse voltage, guys, for a half-wave rectifier, it's given, I'll be with you now, as V peak out. It's given as what? V peak out. Remember, I said V peak out is the same as V peak rectified. What is it equals to? V. Now, what is this peak inverse? It is the voltage which, during reverse bias, this diode must be able to withstand it without breaking down. Why should it withstand it? Because when it breaks down, what will happen? On the negative cycle during the first second, what it will conduct when it breaks down. Now, we do not want that. Now that we'll talk about the peak inverse voltage. How do you know it? Where do you get it? A little bit later. Thank you, guys. Now the next other thing, guys, that we're gonna look at, it's straightforward. It's a circuit which we call it what did we call this transformer? In the previous thing I said to you, we call this a center tapped transformer. Center tapped transformer. Now we're going to do something to this center tap transformer. We connect a diode, we call it D1. And we connect another diode, we call it D2. D1, D2. Remember the voltage here, V peak. When it's positive, how is it here? Negative. When it's positive, how is it there? Negative. When it's negative, how is it there? Positive. This is the center. Remember the voltage here on top there, it's V sec divided by how much? 2. Whatever calculation you have. Remember our V sec was how much, was equals to how much? Let's say we're using a similar transformer with the same turns ratio. It was 11 volts VRMS. Or rather 31.1 V peak. Now what does it mean? V 31.1 divided by 2 is 15.11. Our V peak out would be equals to, if it's the same, V is equals to 15.11 volts. That is our V peak out if this was 10-1. And in South Africa we know that the 220 is standard. 220 standard. Now it means the voltage here from there to there, it's, now have a look, when it's positive, negative, diode D1 is forward bias. When we have our output, it's something of this nature. If this is my zero line, something of this nature. Which diode is forward bias? D1 on. How's D2? Off. In the next cycle, when it's negative there, how is it? When it's negative there, When it's negative there, guys, negative, how is it here? Positive. And how is it here? Positive, how is it there? Now, point C, can you see it depends, you are speaking it with respect to whatever. When it's negative there, it's positive. How's D2? Forward bias, this is what you get. D2 on. How's D1? Off. Now this again, we call this D2 when we repetition of number 1, repetition of number 2. Now again in here, now this circuit here that we have, we call it center tapped full wave rectifier. It's a very interesting circuit. Now dude, we put in an AC there, we have a circuit here which it gives us a pulsating DC. Looking at it again, guys, during this time now, have a look. In this one, F out, look at it, how many cycles do you have to, within the same period as the first one, we've got twice cycles now. F out is equals to twice F in. In other words, all the time when you work with a full wave rectifier, guys, what do you get? If the frequency is twice the input frequency, the output frequency is twice the input frequency, you know your circuit is working nicely. But the waveform must be of this nature. Again, this voltage in here, guys, it would be V peak secondary, or V peak out, V peak or V peak rectified, divided by 2 minus how much? 0.7. Minus 0.7. Very, very important for you to know the peak from there to there. From there to there, which is the same as from there to there, the same as from there. You just subtract one diode and you are able to know how V peak is my V peak out. Are we together, guys? I hope and believe that you are following me. Now, one of the few things that you've got to know about this again is calculating what we call the average voltage. Again, I say to you guys, the V average is equals to, as I said the other day, VDC plus V twice V peak out divided by pi. Now VDC again, you must check your reference point there. If in this case it's no longer my zero is here. What is this part? What did I say we call this part? We call this part a DC offset, meaning in my circuit we've got DC. But again, like I said, when you have something of this nature, if your zero line is this, and this is what you're getting, what is this part? Let's say this is X. From there to X, it's your DC, but from there, it's your V peak out. Now we say twice V peak out. Why do we say twice V peak out? It's because between, on the same period as our one cycle, how many peaks do you have now? We have 2. Therefore, twice V peak out divided by pi will give us our average. In most cases in class, you'll find that you have a situation whereby your VDC is equals to 0. This circuit, like I said to you, we call it a center tap full wave rectifier. Again, it's got a formula that we've got to use. Each V peak, to calculate the PIV, it will be equal to twice V peak out plus how much? 0.7. And this gives you your answer. We're going to talk about, we said the peak inverse voltage, it is a voltage which you must ensure that your circuit can hold on, never crack under it, because once it breaks down, it will allow current to flow. For the day, I'm going to have a look at the last circuit of the day, guys. The last circuit, we call it the bridge rectifier. We call it the bridge rectifier. Now this one, I'm now drawing the secondary only. I'm no longer doing the calculation of the primary to secondary. Look, how do you go about drawing it? open up a space there, I open up another space there, open up a space there, and I open up. How many spaces do I have? Connect my load now. This is the situation I'm having. I have how many spaces? 1, 2, 3. Now I always say to my student, look at it. When you draw the first diode, how is it facing up? I go opposite direction, opposite line there. I've got a diode facing down. Now, facing the same direction. This side, I have a diode following that one, or preceding that one. Look at it. But opposite is facing in the same direction. Now, this is my D1, D2, D3, D4. This is also connected to ground. Let's have a look now. When it is this way, positive, negative, which diodes are forward biased? The positive will forward bias that diode, the negative will forward bias this diode. Therefore, 2 and 3 are forward biased. Now let's have a look at our output. Let's have a look at our output. Now that is the situation. This is what you get. How which diodes are on? D2, 2, and 3. But 1 and 4 are reverse bias. During the next cycle, guys, let's have a look. Negative, positive. Which diodes now are forward bias? Look at the negative would forward bias diode number 1. The positive diode number 4. Current will flow from positive here, go in that direction, and that would be your setup. Which diodes are on now? 1 and 4. Now look again. This bridge, it does the same thing as a center tapped full wave rectifier, but the only difference is that the frequency F out is equals to twice F in. Always you know that this is a full wave rectifier, but again very, very important is that we're going to have a look at now V peak rectified. I said V peak rectified is as V peak out. V peak out. Now look at it. V peak rectified. What is it equals to? It's equals to V peak secondary minus. How many diodes are on it in a given time? 2 diodes, so therefore minus 1.4. Now you're able to calculate this. Take note, always check. If I wanted the negative output in here, what would I do? Connect this diode this way, and this one that way, and those ones the opposite way. Then I'll rectify my negative pairs. Very, very important for you to take note of that. Now another very important, the V average. The V average is the same as that of a center tap full wave rectifier. Now my dear students, what did we look at? We recap quickly. We looked at my first part. We looked at a rectifier circuit. We said it's got what? It's got a transformer, showed you the calculation, a rectifier, and what will we look at into our next lesson? We'll look into a filter, a regulator, and then we'll be complete with this section. Now, on a friendly note, please take note. There are problems at the end of the textbook. As a student, you are expected to visit them, practice on them, and make sure that you hone your own skills of understanding and doing calculation. Now bear in mind that this section until the end, which I think until section 2.5, it will be part of your testing next week Friday. And also take note that next week Friday, when you write a test, it will be here on campus. I appreciate your cooperation, and I know that you are working very hard at home in order to ensure that you are going to be the best you can possibly be. Thank you.